In our first example, let's find the intervals in which this function f of x is increasing or decreasing by looking at the graph of the function. So let's start. How do I find the functions where the graph is increasing? Well, that's when the graph is going up. So it appears my graph is increasing in this area, which is starting at 0 and going to pi over 2. And we don't include the pi over 2 because that is a local maximum point, so it's neither increasing nor decreasing because the derivative is 0 at that point. And our second point, second interval in which is increasing, it starts at 3 pi over 2 and goes to 2 pi. Now we're going to look and find our intervals in which our function is decreasing or the graph is going down. And this would be this area here in red. So I'd say the interval in which the function is decreasing is from pi over 2 to 3 pi over 2. And that's all you have to do on this type of problem. In example 2, it's a 4-part question. I'm going to first start by part A, where we find the critical numbers of f, if they exist. So remember, critical numbers exist when the derivative is equal to 0. So I'm going to have to find the derivative of this function. But before I do that, let's get rid of the parentheses by distributing the x squared, so it's just easier to find our derivative. And using our power rule, we figure out our derivative is 6x minus 3x squared. And remember, critical numbers occur when the derivative equals 0 or does not exist. So I'm going to set this derivative equal to 0, factor out my GCF, and solve each factor. End up critical value of x equals 0 and another critical value at x equals 2. Then I check and see where the derivative does not exist. Well, this is a polynomial, so the derivative always exists. So my only two critical values are 0 and 2. Part B, we're going to find the intervals in which the function is increasing or decreasing. The best way to do this is to make a sign table. So you draw a number line, and on that number line you place your critical values, and that's when the derivative is equal to 0. Now I'm going to figure out if my derivative in between those critical values, or on the ends of each of those critical values, is positive or negative. I don't really care about what the value is. I'm just testing to see if I get a positive or negative. So we want to start with a negative 1. So 3 times negative 1 gives me a negative. 3 minus a negative 1 becomes 3 plus 1, which is a positive. So that means on that interval, I will have negative or decreasing values. Plugging in 1, I get a positive and a positive, positive and a positive. So that gives us a positive solution. So the interval from 0 to 2, my function is positive. Plugging in 3, I get positive and negative, which positive times a negative is a negative. So looking at my sign table here, I can easily see that my intervals in which the function is increasing is just 0 to 2. But the intervals in which the function is decreasing is negative infinity to 0, union 2 to infinity. Part C asks us to apply the first derivative test to identify the relative extremas. So again, to apply the first derivative test, we can look at our sign chart that we made in Part B. So I'm just going to recopy it here, but we've already developed this in Part B. And this look, so it's negative means it's decreasing, increasing, and then decreasing. Where I go from positive to negative, I have a maximum. When I switch my derivative from negative to positive, I have a minimum. So according to this, I must have a relative minimum at that critical value of x equals 0. To figure out the exact value of this extrema, or the point in which this extrema occurs, you would plug in that critical value of 0 into our original function to get our y value. So a better way to say this is I have a relative minimum of 0 at the point 0, 0. We're going to repeat this process for our relative maximum, because again, the first derivative test says you have a relative maximum when your derivative switches from positive to negative at the critical value. So at y equals 2, I end up with 4. So I know I must have a relative maximum of 4 at the point 2, 4. Okay, I'm going to erase some of this for part D. Part D just says us we're going to check our work with our graph. So here's a graph I got from my graphing calculator. So checking my critical values. Remember, our critical values happens at the humps and valleys of our graphs. So that's, you can see those x values of 0 and 2 is where we have a hump and a valley. Now increasing, look how my function here is going up. So that checks us increasing in that interval. Decreasing, so let's look, our function is going down when I read the graph from left and right on this red interval here. That's the negative infinity to 0. And then again over here from 2, starting at the x value of 2 to infinity. So that checks out. The last is, I want to find where my relative maximum minimum. So on my graph, where are my relative maximum points and minimum point? And that's here at the humps and valleys of my graph. So it's very easy to see that I have a minimum and I have a maximum here at this point 2, 4, and I have a minimum at the point 0, 0. So everything checks out, and I think I did good. For example 3, we're going to have the exact same directions, except we're on the interval from 0 to 2 pi. So first we're going to start by finding our derivative. So we take our derivative. Remember to use your chain rule. And then we set our derivative equal to 0. Factor out our GCF of cosine of x. Set each factor equal to 0. Use our knowledge of the unit circle to figure out when cosine of x is equal to 0. So that'd be at pi over 2 and 3 pi over 2. Likewise, use our knowledge of the unit circle. And so we know this has a reference angle of pi over 6. And I know that sine is only negative in quadrants 3 and 4. So the angle who has a reference angle in quadrant 3 would be 6 pi over 6. And in quadrant 4, that would be 11 pi over 6. So this problem has 4 critical values: pi over 2, 7 pi over 6, 3 pi over 2, and 11 pi over 6. And again, because sine and cosine never have derivatives always exist, I don't have to worry about when the derivative does not exist. For part B, to find our intervals increasing and decreasing, we can make a sign chart, putting all our critical values on there in increasing order, and then plug in values in between each of the critical values into our derivative function to determine if we're going to have a positive or a negative. So again, I don't care exactly which value it is, but I'm going to plug it in to see if I get positive or negative. So for example, the first one, I'm going to try pi over 4. Cosine is positive in first quadrant. 2 sine x plus 1 gives us positive, so that's a positive in that interval. I'm going to repeat these for each of the following intervals. Remember, it's only on the interval from 0 to 2 pi, so for my last one, something greater than 11 pi over 6 but less than 2 pi, I'm going to use degree measure. Let's go to, say, 350 degrees. So cosine of x, cosine of 350 degrees is a positive value, and 2 times sine of a positive plus 1 is a positive, so that last interval is also positive. So for my answer, the interval in which the function is increasing, that is from 0 pi over 2, 7 pi over 6 to 3 pi over 2, and finally 11 pi over 6 to 2 pi. Intervals in which the function is decreasing, pi over 2 to 7 pi over 6, union 3 pi over 2 to 11 pi over 6. Part C, use the first derivative test to identify your relative extremis. So we're going to start by, again, looking at our sign table that we have from part B. And recall that when the function is the interval in which the function is positive, we're increasing, and we're negative, we're decreasing. And when we switch from by positive to a negative, that's a maximum. When we switch from a decreasing to an increasing function, we have a relative minimum. Now, since this is a closed interval from 0 to 2 pi, we will also include the endpoints 0 and 2 pi as relative maximums or minimums. So looking at this data, we have some relative minimums at 0, 7 pi over 6, and 11 pi over 6, and relative maximums at pi over 2, 3 pi over 2, and 2 pi. Oh, I just realized something. This is a open interval, so do not include the 0 and the 2 pi endpoints. Our points on our graph, remember our critical values are our humps and valleys. So those would be the 4 critical values at pi over 2, 7 pi over 6, 3 pi over 2, and 11 pi over 6. Next, let's check our intervals in which it's increasing and decreasing. Our function is going up here, here, and here. So that checks off with our 3 intervals of increasing. Our function is decreasing where I've shaded in the red, which corresponds to our 2 intervals of decreasing. Finally, our relative max and mins, disregard that 0 point. Originally, when I first worked this, I thought it was a closed interval. Since it's an open interval, the endpoints cannot be local maximums or minimums. 2 relative minimums, 7 pi over 6 and 11 pi over 6. Next, check our relative maximums at pi over 2, and again here at 3 pi over 2. Again, disregard the 2 pi because I forgot that it is an open interval. Next example, we are given the graph of the function f. We don't know what the equation is, we're just given the graph. And then we're asked to sketch the graph of the derivative. In order to do this, there's certain things that you need to look at. The first thing is you need to figure out where your critical value is. Now remember, critical values occur at your local max and min points. So we notice we have a critical value here at 2. Find the intervals in which the function is increasing and the intervals in which the function is decreasing. So our graph is going down from negative infinity to our critical value of 2, so we know the function is decreasing from negative infinity to 2. And our graph is going up from 2 to infinity, so we have an interval of increasing from 2 to infinity. Now, how does these 3 values, our critical value, intervals increasing and decreasing, translate to our graph of f of x? Okay, let's look at this. We know we have a critical value at x equals 2, so that tells us our derivative is equal to 0 at that point. So we have the point 2, 0 in our graph. Now, when it's a function, interval in which a function is decreasing, our derivative is negative. Interval in which a function is increasing, our derivative is positive. So for decreasing, we need negative values or below the y-axis, x-axis. And for increasing intervals, I need positive values, so I'm doing above the x-axis. Recall that derivative is equal to the slope of the tangent line. And if you notice, values closer to, the x values closer to 2 have smaller slopes, slopes closer to 0. And then when I get up here to my x values away from 2, such as an x value of 5 or negative 2, I have very steep slopes. So that's the reason why I have a large positive or a large negative numbers away from our critical values, but very close to 0 near my critical values. The other direction, our last example, here we're given the graph of the derivative, and we're going to figure out what in the intervals in which the function is increasing and decreasing, and our relative max or min points. So first, here's our derivative. So notice our derivative has critical values when our derivative equals 0. So the 2 points where our derivative graph intersects the x-axis is considered our critical values. So when derivative equals 0, we have critical numbers. So our critical numbers are at x equals 0 and x equals 1. Next, we're going to find the intervals in which our function was increasing or decreasing. So that is, with our derivative is positive, we have intervals of increasing on our original function. If our derivative is negative, we have intervals of decreasing. So when our function value is increasing, when our derivative is is positive. So looking on my graph, I'm going to highlight where my derivative is positive above the x-axis. Therefore, my function is increasing from negative infinity to our critical value of 0, and from our critical value of 1 to infinity. Next thing we'll look at is we know that f will be decreasing whenever our derivative is less than 0. So looking at our graph, we can see we have the intervals of decreasing right in between our two critical values, because that's when my derivative graph is below the x-axis. So we have interval of decreasing from 0 to 1. So intervals of increasing and intervals of decreasing is the answer to part A. To find part B, we're going to estimate the x values. Now notice we only have to find the x values of the relative maximum or the relative minimum. So remember, our relative max or minimums can occur at our critical values. And we know that we have a relative maximum if we switch from increasing to decreasing. And we have a relative minimum when we switch from decreasing to increasing. So therefore, I can draw the conclusion for part B that I have a relative maximum at x equals 0, and I have a relative minimum at x equals 1.